let us consider these two questions. One is matching. Only two columns are given. First column, you can notice 5 systems are given, systems in the form of geometrical isomers, diastereomers, mesoform, erythroenantiomers, and racemates. Now, here, even though some of the terms are quite familiar, some are not. For example, geometrical isomerism or cis-trans isomerism you are familiar with. We have discussed this in the last class. Diastereomers. This term, I think you remember. If there is a mirror image relationship, there are two optical isomers possible, dextro and levo isomers. So, those isomers having the mirror image relationship are known as enantiomers. But there may be two structures which may not be having the mirror image relationship. Two representations of the same compound, but these are not mirror images. If the two structures are mirror images, they are dextro and levo isomers, the enantiomers. But if these two structures are not having the mirror image relationship, then they are known as diastereomers. All right. If the structure is such that one half of the molecule is the mirror image of the other half, then that is known as the mesoform. All these we have seen. E, this also we have seen in the last class. Instead of this term, I have used racemic modification or racemic mixture. Racemic mixture is also known as racemates. Racemates, nothing but racemic mixture. Erythroenantiomers. By enantiomers we know they have the mirror image relationship. But what is meant by erythroenantiomers? Now, for example, let us consider, first I consider D, because regarding this erythroenantiomers I have not mentioned anything. D, correct answer is 5 on the other side. Correct answer for erythroenantiomers, correct answer is this. Answer 5. Now, let us consider the answer 5 on column 2. Probably, since I have mentioned erythroenantiomers, you can notice, suppose I place a mirror here. Between these two structures, I place a mirror. It is obvious. They bear the mirror image relationship. That is why these two are known as enantiomers. But what is meant by erythroenantiomers? For example, you look at this structure. Two hydrogens, they lie on the same side, namely left hand side. If I look at this structure, on the left hand side, to these two, here there is one asymmetric carbon, here another asymmetric carbon, and to these two hydrogen atoms, two hydrogen substituents, lying on the left hand side. And this is the enantiomer of this. If this is the object, this is the mirror image. And you can notice the two hydrogens will lie, both these hydrogens lie on the right hand side. Suppose I replace this chlorine by OH. Instead of chlorine, I put OH here. Then this will have a plane of symmetry here. So instead of chlorine, I put OH. There will be a plane of symmetry, because of which this will become the mesoform. So in two ways you can try this. One is hydrogens lying on the same side, whether on the right hand side or left hand side. These are known as erythroenantiomers. Suppose this hydrogen is placed here, opposite side, one hydrogen left hand side and the other hydrogen on the second asymmetric carbon atom lying on the opposite side, then they are known as threoisomers. So erythroisomers means, for example, as in this case, similar atoms are lying on the same side, either on the left hand side or right hand side. These are erythroisomers, and if this hydrogen is on the opposite side, then that is known as threoisomer. All right. Now let us match. Geometrical isomerism. You can notice which of these compounds will have a double bond. Geometrical isomerism, immediately it should come to your mind that a double bond should be present. Consider this. Here CH3 and H, CH3 and D. So similar groups CH3 lying on the same side or opposite side, cis trans isomerism. So for A, 3 is the correct match. Diastereomers. So again you look for two structural representations. Of course, this already we have seen. Consider 4. Put a mirror here and see whether that will be having the mirror image relationship. It will not. So 4, the pair of compounds which don't bear the mirror image relationship, they are known as diastereomers. So for A, 3 is the correct option. For B, diastereomers, 4 is the correct option. For C, mesoform. Mesoform, consider 1. If you have a plane of symmetry here, top and bottom half of the molecule will bear the mirror image relationship. That is the characteristic feature of the mesoform. D, already we have seen. So only thing that is left out is racemates, racemic mixture 2. Now, if we put only plus within brackets, dextroisomer, only minus within bracket, it is levoisomer. Or if I put both plus and minus like this, it denotes the racemic mixture, or it is also denoted like this. If you put D and L side by side, it also represents racemic mixture. All right, come to question number 4. It is simple. Two compounds are given. Of these two compounds, you have to find out the number of optical isomers possible. For optical isomerism, the presence of asymmetric carbon atom is a must. Consider this compound. Let us see whether it is asymmetric or not. The central carbon is not asymmetric because these two groups out of 4, these two are the same groups. So optical activity is not possible. Not possible means I put 0. Consider these 4 answers. A and D you can omit. But out of B and C, which is correct? So no optical isomer, 0. Consider this a second one, it is asymmetric. But there is a simple rule for finding out the number of optical isomers, there is a simple rule 2 to the power n, which is equal to the number of optical isomers, where n is the number of asymmetric carbon atom. Consider this molecule. It has only one asymmetric carbon atom. The central carbon atom is asymmetric. So only one asymmetric carbon atom. So n equal to 1, 2 to the power 1 is 2. So you will have one D isomer and another L isomer. Two optical isomers are possible. So C is the correct option, 0 and 2. Do you follow?